So it's like a sugar cube. When you dissolve a sugar cube, does it retain its shape? You know, with the sharp corners? Now, when you dissolve a sugar cube, the corners are attacked first, and then the edges. Why are the corners attacked first, or dissolved first? The corners are dissolved first because those are the weakest bonds. Because the corner is only held together by these atoms here, and then it can be plucked off. Versus an edge is going to be held together by more atoms. Right? Versus a face is going to be bonded to the most atoms. And so you're going to attack the weakest first, and the weakest will be the corner. Well, if you have an iron nail like that, you're going to attack the weakest iron atoms first. The weakest iron atoms are going to be on the flattened ends here. And so if we look at A is this big petri dish, and what we have is just an iron nail, so we got iron. But the iron's not all the same. You know, when we look at this flattened pancake of iron here, this is iron. So if the iron's going to be attacked, i.e. corroded, which iron will be attacked first? The nice, pristine, I think is body-centered cubic iron over here, or the highly defective iron over here? The highly defective iron over here. And so this is our anode. Anode is where oxidation occurs. And so at the anode here, we're going to form iron 2 plus and 2 electrons. Those 2 electrons are going to travel to the cathode. Well, the cathode is the same chunk of iron, but it's going to be the pristine part of the iron here. And so over here, the oxygen is going to come in here with water to form, how many hydroxides? 4 hydroxides, so we'll need 2 waters. So the oxygen is going to pick up 4 electrons altogether. So 2 electrons from maybe from here, and then we have another pancaked iron over here, which is going to form iron 2 plus, and then 2 more electrons come in here. And so we'll form 4 hydroxides. So this is the anode, this would be the cathode here. And actually this battery is weird because it has 2 anodes. It doesn't have to be symmetric like this. Both irons can come from the left side, or both irons can come from the right side. Just made it like this. What they did here in the petri dish is they added a drop of phenolphthalein. The phenolphthalein is going to detect the presence of hydroxide. So you can see hydroxide formation around the cathode here. And that's what we expect. The cathode, the oxygen comes in, picks up the electrons, and forms hydroxide. So this whole area should be pink because this whole area is generating hydroxide. At the anode, you can see some green precipitate. That green precipitate is this. Eventually what's going to happen is the hydroxide and the iron 2 are going to meet. When the hydroxide and the iron 2 meet, and which one moves faster, iron 2 or hydroxide? Hydroxide moves a lot faster. And so the hydroxide will move out here, it diffuses a lot quicker, and so we end up with iron 2 plus 2 hydroxides yields iron 2 hydroxide, which is a green precipitate. And so around here we see the green precipitate forming. Now corrosion's slow in DI water because of space charge. There's no salt bridge here. And so what has to happen is the ions have to migrate all the way to the anode to neutralize that charge. Or the cations have to migrate to the anode. The cations have to migrate to the cathode, to neutralize that charge. Well, they do both. The cations start to migrate to the cathode, the anions start to migrate to the anode, and we get a precipitation occurring. It's just that the hydroxides are so much lighter that they move so much faster. Now, salt water, things will corrode a lot faster because we don't have to wait for diffusion to neutralize the space charge. If we have salt water present, then as the hydroxide is being generated, it can be surrounded by, say, for example, sodium ions in salt water. And as the iron 2s are being generated, they can be surrounded by chlorine ions in salt water. And that's going to help stabilize the charge. Eventually, they'll migrate to each other, still precipitate, but immediately the charge is going to be neutralized. Whereas here, we're going to slow things down because we have to wait for the hydroxides and the iron 2s to meet to neutralize the space charge. Whereas a salt water, it would be immediately neutralized. All right, Petri dish B here. This is showing a kink. So you pound the ends flat and then you bend the nail. When you bend the nail, you're going to introduce a whole bunch of defects. You know, you're going to tweak the bond angles and do whatever else. And so this is going to be weak, weak, weak. So the weak iron's attacked first and the pristine iron is going to be left. And so we have 3 anodes here. 1, 2, 3 anodes and 2 cathodes in this particular battery. Have you ever heard of galvanized iron? Galvanized iron is iron that's been protected. Galvanized iron resists corrosion better than regular iron nails. And what galvanized iron is they just coat the nail with zinc. And so here they just wrap some zinc foil around here. And what this does is this. The zinc and iron, which one's easier to oxidize? So let's take a look. Zinc versus iron, which one's easier to oxidize? Iron, because it has a higher potential. Zinc versus iron, which one's easier to oxidize? Zinc. Zinc is easier to oxidize because zinc has a higher oxidation potential. You have to remember, if we're looking at zinc and iron, we're looking at the reverse reaction. If we're looking at the reverse reaction, we have to change the sign. And so zinc has an oxidation potential of plus 0.76 volts. Iron has an oxidation potential of plus 0.44 volts. And so plus 0.76 volts is greater oxidation potential than 0.44 volts. And so zinc has a higher oxidation potential. Well, what's the species that's going to be oxidized? The species that's going to be oxidized is the species with the highest oxidation potential. And so when we look at this, this is what's going to happen. The zinc is now going to be oxidized. And so the oxygen is going to come over here on the pristine iron and try to pull electrons off the iron. But rather than pulling electrons off the iron, which it can, it's going to pull it off the zinc because zinc is easier to oxidize. The zinc and the iron are in electrical contact, so the electrons are going to go from the zinc to the iron to the oxygen. As the electrons leave the zinc, it forms Zn2+. So again, what we see is we see pink around the cathode, but now the cathode is this pristine iron over here, and the anode is not iron, the anode is zinc. And so the reaction is Zn goes to Zn2+. When we form Zn2+, it reacts with the hydroxide because the Zn2+ is going to migrate to the anode, the hydroxide is going to migrate to the cathode. Where they meet, Zn2+ reacts with hydroxide to form white zinc hydroxide precipitate. So if you look closely here, you can see white zinc hydroxide precipitate there, where the ions meet. Here, you can see that what they did was they took the nail and wrapped copper around it. So what's going to be oxidized, copper or iron? Which one has a higher oxidation potential? Copper or iron? Iron. Iron has a much higher oxidation potential. So iron's going to be oxidized. So you can see it here. Iron forms iron 2+. At the copper is now the cathode. And you can see the entire nail is being corroded here. And so we're going to form hydroxide here as the oxygen is being reduced. And over here we form iron 2. And where they meet, the hydroxide is going to migrate to the anode. The iron 2 is going to try to make it down to the cathode, but it's not going to get very far because hydroxide is moving much faster. It's going to form this precipitate, which is a green iron 2 hydroxide precipitate. So here we have galvanized iron. galvanized, the coating doesn't have to be perfect. In fact, there's no problem if there's gaps or cracks in the coating here. Because what's going to happen is you have a choice of oxidizing iron or zinc. We're going to oxidize zinc because zinc has a higher oxidation potential. Zinc gets oxidized, those electrons go to the cathode. The cathode now is iron, where oxygen is going to pick up those and form hydroxide in neutral solution. And so as long as we have zinc here, the iron's protected. We call this, you know what we call this? We call this sacrificial anode. The anode is where oxidation occurs. And so this is sacrificial anode because we're offering zinc instead of iron. Take the zinc. The zinc is easier to oxidize. Right? And so this sacrificial anode. It's also called cathode protection because we want to protect the cathode. The cathode in this case is iron by sacrificing the anode. We don't care if the anode gets corroded. In fact, we want the anode to get corroded because usually zinc is not a structural material, iron is a structural material. And if the iron gets corroded, it's going to weaken the structure. And so we want anything that's easily corroded to act as the sacrificial anode. Yeah, corrugated is usually made out of galvanized, I think. Recall. Okay, we don't have to use zinc, we could use magnesium. Magnesium has an even higher oxidation potential than zinc. And so here you can see sacrificial anodes of magnesium on a boat hull and rudders. What happens is you're sacrificing this, so go ahead and corrode the magnesium. Once all the magnesium is corroded, you just replace it with another block of magnesium. And this should continue to protect the iron underlying here. You could buy sacrificial anodes at Home Depot. They sell them for various applications. Another way of protecting metal is by painting it. You know, if you paint it, then hopefully, you know, well, actually, you see there are a lot of chips in this paint. Wherever there are chips in the paint, you're going to see corrosion. But if you can paint this and seal it, and there's no chips in that, then it should protect the iron because no O2 can attack it. And so that's called an inert coating, inert boundary. We can paint it, and so if this green were paint, but the problem is if there's a chip in the paint, then we're going to see corrosion occur. This is another way iron can be protected, and that is plated iron. This is copper. Copper is fairly inert. So if we copper plate iron, it should protect the iron until cracks or chips develop. If this were a pristine coating of copper, then no O2 can attack the iron. There's no way to balance out the space charge, and there's nowhere for the iron to go. But once a chip or crack is formed, then we're going to get this scenario. Where the copper will always act as a cathode and the iron the anode, so we're going to see heavy corrosion of the iron. All right, that's corrosion. The next thing we're going to look at is electrolysis. Electrolysis is causing non-spontaneous reactions to occur. And so there are like 3 or 4 applications for electrolysis. Actually, like let's say 3. One is to recharge a voltaic cell. So as this cell discharges, you know, this is spontaneous 1.1 volts under standard conditions. As this discharges, the voltage continues to decrease. But what we can do is we can reverse this reaction and recharge this battery. The way we recharge it is by forcing the reverse reaction to occur. The reverse reaction, if the forward reaction is plus 1.1 volts, the reverse reaction is minus 1.1 volts. So what we're going to do is we're going to take the copper and the Zn2 plus and force the electrons to go right to left. In other words, we take the copper and the Zn2 plus and form copper 2 and Zn solid, which are reactants here. Okay, how do we do that? By putting a power source or another battery in here. And so normally the electrons flow left to right. You know, there's copper 2 ions here. The copper 2 ions pull on the electrons through the wire and eventually oxidize zinc. Zinc goes from Zn solid to Zn2 plus, the 2 electrons get fed. But eventually what's going to happen is the copper 2 ion concentration is going to go down, and we're going to plate a lot of copper metal here. And this electrode is going to shrink because it's being corroded, and we're going to generate a lot more Zn2 plus. And the voltage is going to go down eventually to 0. What we can do, though, is we can hook up this power supply here and then suck the electrons backwards. That is, over here on the power supply, we'll put the cathode here. Cathode's pulling the electrons into the power supply or battery. And so as it pulls in electrons here, it's going to oxidize copper. Copper gets oxidized to regenerate copper 2 ion here, our oxidizer. And then the electrons are forced out of our power supply. When they're forced out over here, they're going to reduce Zn2 ions. The Zn2 ions are going to accept 2 electrons and replate out zinc metal. And so basically we're just reversing that earlier reaction here. That is, we're stripping electrons from copper using the power supply and then giving them to Zn2 plus to form Zn solid and copper 2. So that's the electrode. Well, what kind of voltage do we need? We're going to need a voltage greater than 1.1 volts in order to do this. So in other words, the electrons want to flow this direction via 1.1 volts. And so what we have to do is we have to push back on the electrons with 1.1 volts. If we push back with 1.1 volts, then there's no current flow. And so we need a voltage greater than 1.1 volts to push the electrons in the reverse direction. So there are complications. This overpotential is the excess voltage we have to add to force the electrons to go backwards. And sometimes they're competing reactions. That is, when we strip the electrons away, they might not strip it from copper. There might be a better reducing agent in there. And so we might not get the exact same reaction in the reverse direction as we had in the forward direction. So there might be competing reactions. Non-standard states is always a problem. So nature of electrodes, electrodes might not crystallize. Like if you had a nice slab of zinc metal, when you reform the zinc metal from the zinc ions, it might look like a furry precipitate coating on the electrodes rather than a solid metal coating. And so sometimes those reactions are hard to reverse. All right, that's one application. One application is recharging secondary batteries. Another application of electrolysis is to generate reactive elements or process metals. And so generating reactive elements, we'll just do an example here of an electrolytic cell. Electrolytic cell, the one we saw was just from a battery, so it had 2 beakers. But we can have an electrolytic cell with just 1 beaker. And so what we're going to do is we're going to electrolyze salt water, sodium chloride AQ. Here. Sodium chloride AQ, it's not going to react. So we'll put 2 electrodes in here, and we'll put the power supply like this. The power supply usually has an adjustable voltage. The higher the voltage, the stronger the pull on the electrons over here. And so what's going to happen over here is we want the electrons to be fed backwards here, right to left. And so at this end of the power supply, we're sucking in electrons over here. And so over at this electrode, we're going to have oxidation occurs. Oxidation occurs at the anode or the cathode? The anode. So the anode is over here. We're going to get oxidation. And this is going to be the cathode of the power supply we're going to attach it to. And so what gets oxidized? Well, what's going to get oxidized is we look at what's present. And so the species that's going to get oxidized will have the highest oxidation potential. And so let's inventory the solution. We have sodium ions, chloride ions, and water. So what's the species with the highest oxidation potential out of those three? What has the highest oxidation potential? Sodium?
Where's water?
Oh, here's water here. Can I use that one? Yeah, it's the wrong way. Here's water here. Oxidation, but this is a chart of reduction potential, so oxidation potential is backwards. So here's water with an oxidation potential of what? Negative 1.7 volts. Here's water with an oxidation potential of negative 1.2 volts. Which one should we use? The negative 1.7 or the negative 1.2? Negative 1.2 because that's a higher oxidation potential, right? So that should be the one that's oxidized. Let's go down and see if we see any other water. I don't see any other waters. So the oxidation potential of water is negative 1.2 volts. I'm not going to write all the digits. You should write all the digits down. All right, let's look at the next one here. Maybe chloride. What's the oxidation potential for chloride? Positive or negative? So we look at the oxidation potential for chloride. It's negative 1.358. Water, I'll just write out all the digits. 1229. All right, that leaves sodium ions. What's the oxidation potential for sodium ions? So we go positive 2.7. Is that right? Is that right? Actually, no. It's not right. This is the oxidation potential, not for sodium ion. It's the oxidation potential for sodium metal. The oxidation potential for sodium ion is what? It's gonna be negative. It's gonna be negative something. Might be positive, I don't know. But the oxidation potential for sodium ion is well, you know, oxidation potential is the reverse, so this is plus 3 volts, right? Not like lithium. You know, the oxidation potential for fluoride is what? Negative 2.8 volts. Very low oxidation potential for fluoride. Why? It's hard to oxidize. But do you know what the oxidation potential for sodium ion will be? The oxidation potential for sodium ion is, if this were the chart here, we're going to have to drill a hole through the ceiling and through the roof, and we'll have to extend the chart up into the sky because the oxidation potential is so, not high, so low. It's so low because of this. The oxidation potential for sodium metal is high because sodium wants to lose electrons to form sodium plus. So this has a pretty high oxidation potential. But what is the oxidation potential for sodium ion? Well, we have to remove an electron from sodium ion to form sodium 2 plus. The difference is, this is for a valence electron. Now we're trying to oxidize not a valence electron, we're trying to oxidize a core electron. A core electron is about 10 times more difficult to oxidize. And so if this were, let's say, 2,000 joules, this would be like 20,000 joules. And therefore, the oxidation potential is going to be so low, it's off the chart. It's very, very low. It's going to be a heck of a lot easier to oxidize fluoride, because fluoride, that's in the valence shell. It's not a core electron. And so even though fluoride doesn't want to be oxidized, it's going to be a heck of a lot easier to oxidize fluoride than sodium plus. How often do you see sodium 2 plus? Never. How often do you see fluorine? Well, once in a while, no problem, right? There's a huge difference. And so what we say is it's not even on the chart. It's so low they don't even bother putting it on the chart because why bother? It's not going to happen. And so which of these species will be oxidized? So this power supply is trying to oxidize something. I'm going to try to oxidize the thing that's easiest to oxidize, which will be, why water? Yeah, because the water has the highest oxidation potential. And so whatever has the highest oxidation potential is going to be oxidized by the power supply, trying to suck electrons out. But that works for everything. For everything, you're going to oxidize the species with the highest oxidation potential, except for one exception. And this is it. The one exception is this. Chloride turns out to be oxidized even though it has a lower oxidation potential. And the reason that chloride is oxidized is because of kinetics. When you oxidize chloride, you just pull off an outer shell electron. It's not difficult. Pull off an outer shell electron. Even though it's more work, kinetically it's less because to oxidize water, you have to break bonds and you have to make new bonds. Because to oxidize water, we've got to form O2 and H+. And so we're breaking bonds and forming new bonds. And so what happens is the activation energy to oxidize water is much higher, even though you'll get some of that energy back. Whereas the activation energy to oxidize chloride is very low. And so this has a very low activation barrier because you're just plucking an electron off the outermost shell. This has a much higher one. And so, you know, initially you'll need a much higher voltage to oxidize the water, but in the end you'll get some of that energy back. And so what happens is chloride gets oxidized. And so this is the only exception that you have to remember. Even though chloride has a lower oxidation potential than water, when it comes to chloride versus water for oxidation, chloride wins. You know, chloride is gonna, but everything else, you know, everything else is simple because everything else is the higher the oxidation potential, the better. And so what's going to happen here is the chloride gets oxidized. Chloride gets oxidized, 2 chlorides come in here, and we form chlorine, and then the 2 electrons get sucked into the power supply here. Well, what's going to happen to the chlorine? Well, at the cathode, this chlorine here is going to be bubbled out of solution. So we form chlorine gas over here. Okay, so at the cathode, we form chlorine gas. What happens at the anode? Oh, sorry, no, this is not the cathode. This is the anode. At the anode, we form chlorine gas. Oxidation occurs at the anode. And so this is anode. What happens at the cathode? Reduction. And so what are we going to reduce? The species with the highest reduction potential. So what's the reduction potential for sodium ions? Let's take a look. Yeah. The reduction potential for sodium ions to form sodium metal is negative 2.713 volts. So this is negative 2.713 volts. What's the reduction potential for chloride? What is the reduction potential for chloride? I need to scroll up here. Here's chloride. What is its reduction potential? 1.358? Negative 1.358? No, you're right, that would be oxidation. It's off the chart. In this case, what we have to do is drill a hole in the ground to continue the chart down into the ground, because the reduction potential is going to be way lower than even lithium ion. It should be below negative 3 volts, somewhere way down there in the ground. And so what we say is that the reduction potential for chloride is very, very low. It's so low they don't even put it on this chart. And the reason is because where does that extra electron go? And so chlorine goes to chloride. So we know the reduction potential. Chlorine goes to chloride. The reduction potential for this is negative whatever volts that was. But chloride goes to, what do you even call Cl2 minus? If Cl minus is chloride, what is Cl2 minus? So we have chlorine, we have chloride, and what should this be called? Double chloride, or? No, it's not dichloride because it's not two chloride. Chloride with a double negative charge? Is that what we should call it? Actually, we don't call it anything, because how often do you form this? Never. Why do you never form this? Because the reduction potential is very, very low. It's so low, we got to dig a hole in the ground to place it, right? So this isn't going to happen. It's too low of a reduction potential, because that extra electron is going to go where? Into the next higher energy shell, which is totally unfavorable. And so what's the reduction potential of water? Well, here's the reduction potential of water. Minus 0.828 volts. Actually, this is the only reduction potential for water. If we scroll up, there's no other waters. And so what's going to be reduced? No, there's only one exception. Chloride and water. No other exceptions. So what's going to be reduced? Water. Why? Because water has a higher reduction potential. And so over here, water is going to react at this electrode and generate hydrogen gas. So as we generate hydrogen gas over here, we have to make sure the hydrogen and the chlorine stay apart from each other. And so we have to build a little wall here. If we don't have a little wall here, we're going to have an explosion because the hydrogen will react with chlorine explosively.
There was an explosion in my chemistry lab. I think it has to do with the chloride and the gas concentration in Hawaii.
Oh yeah,
Did you hear about that?
yeah. So there was an explosion in Hawaii, and unfortunately, she lost her arm, right? She lost an arm. It was hydrogen gas. It's some kind of bacteria or something. Yeah, some reactor. University of Hawaii. Yeah, that's too bad. All right. So this electrolytic cell, we can generate hydrogen and chlorine. We just have to apply a voltage. So we add up the two potentials, and we get around negative 2.2 volts. And so this is negative 2.2 volts, which means we have to crank up our power to positive, greater than 2.2 volts. And then we can force the electrons to go backwards, because electrons are trying to go forward. Actually, electrons aren't trying to go forward here, because nothing's happening. But we got to crank up the voltage to 2.2 volts to get this to go. Okay, what if I wanted to make, I didn't want to make hydrogen and chlorine, I want to make sodium and chlorine. In other words, I want to reduce the sodium ions rather than, I want to reduce the sodium ions rather than the water. How can I do that? I can get rid of the water. If I get rid of the water, what's going to be reduced? Sodium or chloride. If I get rid of the water, sodium ions will be reduced. And so how can I get rid of the water? How I can get rid of the water is don't go AQ here, go NaCl liquid. So I'll take pure sodium chloride and melt it into sodium chloride liquid. And if there's no water around, then I don't have any choice. I got to reduce the sodium ions, sodium metal. And so this is what's happening here. We can generate sodium metal and chlorine gas in a reactor like this. Well, we could do the same thing if we just use molten sodium chloride, i.e. in the absence of water. Okay, there's also electroplating. Electroplating is you're just feeding a current. So if we had copper 2 ions in there, we could reduce that and plate whatever electrode we put in there at the cathode. So this is electroplating. You can read about it. Look. Okay, the final section of this chapter deals with stoichiometry. And the stoichiometry is, we could use the moles of electrons to do stoichiometry calculations. So, for example, here, if I'm electroplating copper, I take copper 2, add 2 electrons to form copper solid. And so I can figure out, for every mole of electrons, I'll precipitate out half a mole of copper. 2 moles of electrons, a full mole. And so we just use this as stoichiometric coefficient, or stoichiometric ratio. Well, how do I figure out how many moles of electrons? The way I figure out how many moles of electrons is I use the Faraday constant here. But then, how can I figure out how many coulombs I have? Well, in order to figure out how many coulombs I have, I use an ammeter. An ammeter measures current. It measures the number of amps. And 1 amp is defined as 1 coulomb of charge passing by in a second. And so let's say I have 60 seconds of 10 microamp. Micro is kind of small. Let's go 10 milliamp current. If I have 60 seconds of 10 milliamp current, that means 60 seconds times 10 times 10 to the minus 3 is a millicoulomb per second. And so the seconds cancel and I get 60 times 10 to the minus 3 coulombs. And then I can use Faraday's constant, 96,485 coulombs per mole. And so I can figure out how many moles of electrons just pass through. Once I know how many moles of electrons, I can figure out how many grams of copper I expect to deposit on the electrode. So I could do stoichiometry like this using these conversions here. And so there's a little bit more about electroplating. Unfortunately, they aren't on the PowerPoints, but they're in the homework, so about keeping the concentration of the copper tube down low. All right, we're going to take another break, and then during this break, can you check out a model kit? Because we're going to do chapter 24, a lab, next. Everyone needs to check out a model kit, but you're going to work in groups because we don't have enough.